All right, in this problem, we are talking about life expectancy from birth for people in the United States based on the year that they were born. So we're given the year, we're given the lifespan for the person that's born in each year. We're going to do the same thing. We're going to let X represent the years after 1900. So that's the first thing we're going to do here. And then we're going to graph these points. I'm just going to list my X values just as they look. Remember, this is a year across the bottom. So my y-axis is the lifespan. And notice I started at 50 and then counted by fives. Again, there's more than one way to count your y-axis, but we want to use as many of those tick marks as possible and just get that data nice and stretched out. And then determine, does this look exponential, quadratic? To me, this is most resembling a straight line. There's a little bit of a curve to it, dips a little bit, but it's still mostly linear. It's trending upward. For the most part, it's not going down. So we're going to draw a line of best fit. You're not going to be able to draw a line that perfectly hits many of those points. So this function's linear, which is the question asking on number 2. And then we're going to determine the equation of best fit. You can either reset your calculator's memory, or if you go straight to stat edit and you have data in there, do not hit the clear button, or sorry, the delete button. Instead, you want to scroll up to L1, highlight L1, press clear, and then down. And that will clear out the list. And then our X's go in L1 and our Y's go in L2. And then we're going to put our Y values in to L2. All right. Again, make sure you have the data in there. Double check it. We're going to go to y equals. Plot 1 is already highlighted, but we need to clear out the last equation. If you still have one in there. And you need to hit zoom 9 again. Oh, hit the wrong button. There's zoom 9. They have their data stretched out a little bit better than us. And theirs looks a little bit more linear, actually. And that's because they counted really by a better number on the X and Y axis. So we're going to hit second mode to go back to the main screen. Now we need to determine the equation. We're going to use the graphing calculator to approximate this. So stat calc. This time we're going to choose number 4 for linear regression. Calculate. When we write the answer, we don't need to write down every single decimal. So our slope is 0.29, round to 2 decimal places. Our y-intercept is 50.82. So we can go ahead and answer question 4. What does the graph imply about the year that you were born and how long you'll live? Well, the slope is a positive number, so that implies that your lifespan is increasing the later you were born. So word that how you like, but your lifespan increases if you were born in a later decade is basically what it's saying. We want to go ahead and get our equation in y equals so we can answer questions 5 and 6. So go to y equals. We're going to press the vars button. and then choose number 5 for statistics, and then scroll to the right to where it says regression equation. And that way we don't have to type in all those decimals. And when we graph, we see a line is a pretty good approximation of this data. Not perfect, but close. So question 5, according to the line of best fit, when would the average person being born live to 65? So this is our lifespan. So that's our Y value. So we're going to use the table to approximate this. So hit second graph. We want to find when the Y value is at 65. So you might start scrolling down. It's going really slow. Remember, you can hit second window and maybe type in a bigger number so you can get there more quickly. See, we're getting pretty close. And it looks like when X is 49, the lifespan has increased to over 65. So remember, X equals 49 is actually the year 1949. So that's our answer to number 5. In the year 1949, average lifespan is at 65 years. Now here, they're asking, what would your lifespan be if you were born in the year 2000? So X represents your birth year. But remember, 2000 is actually X equals 100, because that's 100 years after 1900. So we need to go to our table, second window, tell our table to start at 100, and then look at the table, and then we can see in the year 2000, the lifespan is expected to be about 79.9 years. We're not obviously solving this algebraically. We could substitute 100 in for X in our equation, but I think the table is going to give us a more accurate answer here. So that's an approximate 80-year lifespan. If you want to write 79.9, it's perfectly acceptable. I encourage you to try this last one. Go and try to create the scatter plot. Pause the video now. You'll want to do the same thing here. You'll want to change your years to years after 1900. All right, so the scatter plot should look something like this. So this appears to be a quadratic model, would be the model that best fits this data. So now try to go ahead and determine the equation of curve of best fit. Pause the video, try it now. All right, so the data's in there. So we're going to go stat calc. This time we're going to choose number 5 since it's quadratic regression. And that should be the equation you came up with on this one. And then we want to clear out our data. Make sure you did zoom fit. We're going to go we're going to go to vars number 5 and get our equation in there, and then we can start answering these questions. Number 3 wants to know the least number of homicides. So we're going to hit second trace. And we're going to go to number 3 for minimum. This is a review from your quadratics unit. You can also use the negative b over 2a formula. That would work as well. But we need to go to the left of the lowest point, hit enter, and then go to the right of the lowest point. Hit enter. We don't want to guess, so hit enter one more time. There's our minimum value. So the least number of homicides, remember, homicides are represented by the Y variable. So 6,803. We'll round down to the lowest number. It's evident on the graph, it's the lowest point, that's the vertex. This one wants to know the domain and range, the algebraic domain and range. So that's just a generic domain range. So the domain, quadratic. So the domain is all real numbers. Or you can say negative infinity to positive infinity. The range, this one has a lowest y value. And we know the lowest y value is approximately 6,803. Should be a bracket around that number. And it goes up forever. There are various answers you could say for a real life domain and range. So for years, I'm going to put start at the year 0. Or in other words, remember that represents 1900 because that's where our data was collected from, starting from the year 1900. And our largest year that we put in there was 1970. So this model's good through at least the year 1970. So you could put 70 here. I'm going to go ahead and put 100 for the year 2000. I'm going to say this model's still going to be fairly accurate through the end of that 20th century. Our range. So our real life range, I'm going to still keep it at 6,803 as the lowest value. But of course, homicides aren't going to increase to infinity. They're not going to keep increasing forever, at least let's hope not. So our largest homicide value was at 16,848. I'm going to go a little bit above. Again, there's various correct answers here. Reasonable minds can differ here. Our y-intercept is where x is 0. So we look at our table. When x is 0, the y value is 56,393. And when x is 0, really that's talking about the year 1900. So in 1900, there were 56,393 homicides, at least according to this model. This one wants to know what is the y value when the year's 1976. So we're going to look in our table. When x is 76, find the corresponding y value. So at least according to this model, there were 21,620 homicides. And then finally, they want to know what year the homicides eclipsed 20,000. So we need to find what year the homicides are right around 20,000, and it appears right here. But really, it's going to eclipse 20,000, or it's going to hit 20,000 twice. Really, 1923, it's at 20,000, but that's before our data began to be collected. So you could say 1923, but really you could say, okay, it's going to come down, it's going to reach its minimum value, but then it's going to come back up, and it's going to hit 20,000 again in the year 1975. So I think that's the answer they're looking for on this particular problem. Although, again, 1923 would probably be a good answer as well to this problem.